Hello, welcome to another Step 432 video. This video is going to be an example of an R tutorial type video. So the last video, we sort of introduced the concept. This video, we're going to use it inside of R to accomplish a task. So what I'm going to try to do is sort of recode up an example from the book from scratch. So for reference, let's see here. I'm going to be doing this example from chapter 2. Again, I would note that before watching this video, I basically assumed that you watched the previous video and read this chapter. So in addition to everything that was in the last video and everything I'm going to say in this video, there's a bit more detail in this chapter. I kind of hope you read it. I wrote it. I spent a ton of time writing it. So yeah, I hope there's some value there. But most importantly, beyond reading it, is that you try out the code. So this is one of 3 examples of sort of like going through the steps from this chapter that exist in this chapter. I'm going to go through one of them. Maybe you sort of repeat what I'm doing here for one of these other examples. Right. Okay. So what I'm going to try to do is go through a bunch of stuff that exists in there. I'm going to try to do it without looking at the code myself. That is important because you'll see me make mistakes, which I think is valuable because I think a lot of folks are intimidated by the coding aspect of all this, but I want to show that even, let's see, I first encountered R in 2007, and I still make errors every single time I code. So I want you to see that. And more important than that, I want to see how I recover from those errors. So I'm taking a big risk here because if I run into a problem that I can't fix, it's going to look really silly in this video, but I think that's important. If you see me glancing off this way, that's because I wrote some notes to myself to make sure I don't forget anything. This might be a bit of a lengthy video. Okay, so we're going to do an analysis of this credit data from this package. Before that, I'm going to load one package, but not really. So what I just did was I loaded the tidyverse, and that loads a lot of packages. In particular, these 8 packages here and any of their dependencies. Yeah, so we're not going to teach the tidyverse in this course. We're going to occasionally pull pieces out of the tidyverse because they're useful. But I don't expect you to be some sort of master of the tidyverse. Occasionally, we'll use ggplot2 for plotting, but honestly, I'm still a base plot function person myself for the most part. That's where my comfort zone is. I love tibbles for reasons we'll see in a little bit. Occasionally, we'll use dplyr for a little bit of data manipulation. I might illustrate how to use purrr, but we might use the old school approach of the apply functions a little bit more. And I want to note that when you load dplyr, it masks some functions from other packages, but that shouldn't be a problem. We might use the reader package when we load some data later, but we'll deal with that when we get there. Okay, so that aside, we now have some packages loaded. I generally like to load packages before I do analysis. We might talk about that later, but there's reason for that. Okay, so we ultimately want to look at this credit data set from ISLR. So ISLR is a package for the book, Introduction to Statistical Learning with Applications in R, I think is the full title. That's where the R part comes from. So what I first want to do is look at the documentation for that. So I need to, I'll put myself up here for now. Right, so 2 things. First, note that this syntax here, this : syntax, that's to say pull this credit object out of the ISLR package, but don't load all the stuff in the package. This is the only thing we want from there, so no reason to load the whole thing. All right, so what is the analysis we want to do here? So we have this data on credit card balances. And if you read the book, I sort of put a story around this data. One thing you should note is this is simulated data, so it's not real. So any conclusion we draw from this, you cannot use in the real world. But anyway, so the story I kind of concocted here is that you, say, work at or own a very small bank, maybe say like a local credit union. And you're in the business of loaning people money, either through something like a credit card or a home equity loan or a mortgage, any of these types of instruments where you, as a person sort of doling out money, well, you want to know how risky that is. Because if you loan too much money to too many risky people and they don't pay it back, your bank goes under, and now no one has money. Okay, so that's a problem. So you want to avoid that. So one of the many ways that people assess this risk is through credit ratings. So there's these various agencies, I guess you would call them, that track people's credit score. And a bunch of stuff goes in it. But what pops out is a number between, I forget, it's like 0 and 800 or whatever. The higher, the better. So low credit score means it's a risky lender. High credit score means they're probably going to pay it back. So the problem is the banks, like you as a tiny little bank owner, you don't have that information. You have to buy it from these agencies. So wouldn't it be nice if you didn't have to pay for that? So because you've already given out a bunch of loans, you have information, both demographic information about your customers, information about their accounts with you, and you have the credit ratings from when you bought them. I'm going to smooth around some edges of this scenario, but bear with me. So wouldn't it be nice if, given the information you already have, you reverse engineer some way of coming up with this credit rating, effectively getting it for free for future customers because you reverse engineered it based on the data you have for your current customers? I make no moral or legal claims about whether or not this is something you should do. You probably shouldn't. I'm guessing there's an issue with this somewhere, either legally or ethically, but I leave that to you for now. But I note that you should always consider those things. So we have this. We have this credit rating. We have folks' income, the number of credit cards they have, their age, education, various demographic information. For example, their gender, whether or not they're married, their ethnicity. I pause here to note let's jump to the end here. Let's say we end up with a model that, based on the gender variable, we can tell that for one gender it's sort of on average giving one rating, and for another gender it's on average giving another rating. The question I ask is, should we use that model that way? It's something to think about. Like, is there any reason to give better credit ratings to one gender than the other? Is it because of their gender, or is it because of a bunch of other factors that are related to gender that are beyond their control? And then you really shouldn't be using those to justify how much money you loan to them. I'm probably not even articulating this correctly, but what I want to say here is there's a growing field within machine learning called fairness. And we have to dive very deep into machine learning to get into this, because first we have to understand the basics of machine learning, then think about models that can explain why they're making their predictions or doing it, and then go like 3 layers deeper. But I just want to plant that seed right now to say that there is a lot of moral and ethical dilemmas with using these models. Like, should we build this model that I'm talking about? Now, should we allow for certain variables to influence it? And then it gets even worse. Okay, well, so we say like, well, we shouldn't change how we loan money to someone based on their gender, and then we remove the variable. Well, guess what? This variable is correlated with a bunch of other variables, so whether or not you directly include that information in the model, it's probably going in the model. It's a very difficult problem. People are working on it, but it's influencing our lives right now, whether we know it or not. There's a huge digression, but I think if we're teaching machine learning, we should teach some of the cautions of it. Anyway, so back to our original sort of scheme here. We want to reverse engineer a way to develop these credit ratings. Okay, so the next step would be to note why I'm using this as tibble thing here. So what I'm going to do is I'm going to run the code without the tibble. And this is a bit annoying because actually I'm going to make it more annoying first because you might not have as high a resolution as monitor as me. So maybe when you run it, it looks like this. So that's pretty uninformative. So here what I have is observations 63 through 83 of the last column for which I don't even know its name. That's kind of not helpful. So if I make it a tibble, aha, this is much nicer. It gives me the first 10 rows for which I can see the names of the variables, and it shows me their types. We have some integers, some doubles, and some factors. I pause. Something I mentioned in the book is that we're basically, for at least the first half of this course, going to make sure that our variables are always either numeric, which includes integer and double, or factor. And if it's something else, we're going to coerce it to be one of those. That'll simplify our lives a lot. Also note that it only displayed the columns that it could. So it displayed these columns, and then at the end here it says, well, there was one more variable I couldn't squeeze into your screen. So instead of doing that weird thing where I, make it terrible, I'm just going to suppress it. If I sort of rearrange my windows a little bit and rerun this, we're good to go. Okay, so I'm going to read in the data like that. We now see it here. If we hit this drop down here, we see a bunch of information, in particular, the types of variables here. I would also note that if we click it, it opens the view window here inside of RStudio, which we can do a lot of nice things like sort it. So very quickly, I can see that there's an individual in this data set that has 9 credit cards. I don't know why. I think you can do some filtering type stuff. So like, let's say if I do something like this looks like I filtered to folks with more than 14 years of education. This is a pretty nice screen. I find it to be pretty useful. Okay, what's next? Oh, okay, so there's this ID variable here, and it's very clearly just the row repeated. So I'm gonna remove that. Obviously, it shouldn't be helpful for predicting. And rather than just remove it from all the models we're going to fit later, I'm simply just going to remove it from the data set. So I'm going to do credit, whatever that was, and then I'm going to say select, except that's spelling sleep, select minus ID. I'm going to run that once. That's what it returns. So now I'm going to go back here and store it, and we'll call this data prep. Okay, so quickly, this is a little bit of dplyr to make that happen. We're not going to get into it. There's other ways to do this. If you're familiar with other ways of removing a variable from a data set, go ahead. But for the first, at least half of this class, we're not going to have you do any of the data prep. We'll do it for you. So no worries if this doesn't mean anything to you. I should probably finish the word prep there. Okay, what's next? Okay, so the whole thing we were talking about this week was fitting linear models for prediction. And we developed this case that said, well, when we're doing predictive models, we want to fit it to some data, but then evaluate it on some other data. So what we need to do here is split up our data. So I'm going to do that from scratch. Okay, so what I want to do is first look at the size of this data set. So there are 400 observations in there. And now I want to use the sample function. Okay, so what did this do? What the sample function does is it samples from 1 to this, a size of 400. So basically it shuffled the numbers 1 through 400 randomly. Except I don't want 400 of these. I want, let's see, size. I want 0.80 times n row of credit. So that did the same thing, but now it only returned 80%. I just want to quickly check that I'm doing this roughly the same way that I did here. Okay, because I don't want to confuse you. Okay, so one thing you might note now is I can keep doing this and I get different answers, and that's going to be a problem. So along the way here, I'm going to set a seed, and I want to look back one more time. I want to set the same seed. Okay, 1. Okay, so notice now, if I continually run from the seed down, I get the same result. So that's important to keep in mind. Okay, so why am I doing this? So these values are going to be what I call the train index. So now that I've done this, and remind me too when I'm done. How could you remind me? You're watching the video days later. I need to remind myself that after I do all this code and check it, I want to run from the seed down. But anyway, so what I have stored here is a bunch of row numbers. So if I take the credit data and subset to those particular rows, this would be a training data set. So what this is saying is that take these rows from this data set and return it. So here we only have 320 rows, which is 80% of 40. So I'm going to call that the training data set, if I could type. Okay, I'm going to use slightly shorter variable names in the video just to make my life easier, but you should be able to see a one-to-one correspondence to what I wrote in the book. Okay, so to create the the test data set, I simply do the same thing. Boy, I'm not typing well tonight. Except instead of doing this, I now do the negative of that. Okay, so let's run this real quick and see what we see. So now the training data set has, the training data set has 320 observations. The test set has 80 observations. That's wonderful. So this train index is what sort of controlled that. So if we look at the training data set real quick, this row here is the 324th row from the original data, and so on and so forth. Okay, so I'm going to make a comment here that says test train split data. Okay, so now what do I want to do? Well, I want to what I call the estimation validation split data. So I mostly want to repeat this step, except without the seed. Actually, let's pull this out here. Okay, that's a little easier to read. Okay, I want to repeat the same process, except we're splitting within the training data set. So anywhere that this credit appears, it should now be train. This is no longer the index of the training rows, so the index of the estimation rows. So this data set is the estimation data set. This data set is the validation set, and I should probably put this here and put this here. Okay, like I said, I'm going to run all that now. And let's see. The estimation data set is 256 observations, which sounds to me like 80% of 320. And 64 in the validation set is 20% of 256. That all sounds good to me. We split the data. Okay. So now I want to do this business of look at the data. And I'm going to say this a lot, and it might not mean a ton at first, but later on when we do analysis, it should mean a ton. And we kind of have already peeked at the data a little bit in order to take out this ID variable, but we really haven't made any decisions, so I feel okay about it. So I note that I don't want to look at the test data. So before we even do it, our whole idea here is we're going to fit a bunch of models to the estimation data. We're going to check how well they work on the validation data. And then whichever one works best, we're going to fit it to the training data, and then give one final performance evaluation based on how that works on the test data. But we don't want to look at the test data until then, or else it might influence that and make it look better than it really is. So I want to look at the training data. So one of the ways you can look at the training data is just by outputting the training data. There's a bunch of things to quote unquote look for here. One of the first things I would look for is like, well, we want to predict this rating variable. What kind of data is it? Well, it's numeric, so we're doing a regression task. I also see the types of my other variables. That'll be somewhat important. But that's about all I can get from here. I get some size information. I have 320 observations, 11 variables. That's all good to know. There's some noise in the background, but hopefully this microphone's not picking it up. An alternative way of looking at this is using the structure function. It basically gives you some of the same information. One thing that this gives you that the previous didn't is that these factor variables, it tells you what the levels of them are. That's generally good information to have. Looking at my notes, I noted that if you click one of these, it pulls up the viewer. Oh, we weren't supposed to see that. We don't want to look at the test data. I'm sorry. Forgive me. But like, let's say I wanted to look at the training data. If you use capital V view, that's what pulls that up inside of RStudio. This is an RStudio specific command. I can't guarantee that if you capitalize the V here, it'll do anything if you're running R in a console. I don't recommend that though. What else? Aha, there's this cool package called Skimmer. And if I do skim of train, it gives me a bunch of information that's actually really nice. So like I said, there's 320 observations, 11 variables, 4 of which are factors, 7 of which are numeric. I'm already really liking this. Here's the summary of those 4 factor variables. We see that there's none missing. We have no missing data here, which is kind of nice. That won't always be the case. We see that there are, for example, 287 non-students and 33 students. 196 people are married, 124 are not, so on and so forth. That's pretty cool. For the numeric variables, again, we see no missing data, 100% complete that is. We see their means, their standard deviations, some information about the quartiles, and these cute little histograms that are written right into the console. I think that's neat. So already we're getting a ton of information. But what if we wanted to do things a little bit more visually? So if you've done a regression class before, you've probably looked at a pairs plot, which will take a second, but it looks like this. And I'm going to zoom in. Yeah, so this is okay. There's some things I don't like about this. For example, like these categorical variables, I don't think that's the best way to plot them against numerics. It's just generally visually not all that great. It is quick to plot though, and you can get some information for it. So like right away, we see that rating is super tied to limit, which is something we're going to return to at the end of this. But yeah, so I want to do something else. So there's this package called ggally, and within it, there's a function called ggpairs. And I could run this, but I'm not going to because it's going to take way too long because it's very computationally intense. Instead, we can just go to, in the book where I already ran this, and look at this image. Okay, so let me hide myself for a second here. Okay, so kind of nicely, something I did here is I put rating on the bottom row. So what this is, so for example, this plot here is income as the X variable and rating as the Y, and so on and so forth. So this gives us a lot more information. I would say the diagonals, by the way, are just a histogram or box plot of the variable itself. We're not going to talk about this too much, but I think 3 things stand out to me above all else. Income, pretty strong correlation with rating. Limit, huge correlation with rating. And balance, a decent correlation with rating. So when we're developing possible models, we should probably use a model that considers those. I'm back. Okay, back to the book for just a second. So notice that if you're reading the book, you're like, oh, yo, there's this plot. How do I do this plot? To which I say, oh, scroll to the top, check out the first section, which always will list the packages you need and the source right here. This is the R Markdown file that created this chapter. Any code you don't see in the render document, it's in there. I like to hide the plotting code because it's not teaching you about machine learning. it's kind of a side thing. But if you ever want to see how I made a plot, it's in the source. Have a look. Okay, back to RStudio. What were we talking about? Okay, right. It's time to fit some models. Okay, so I'm going to fit 5 models, but I'm going to start with a very important model. So I'm going to call it mod 1. Again, I'm going to use slightly shorter variable names just for the sake of I'm already screwing up so much of my typing. Here we go. So what I want to do is we're trying to predict the rating variable. So that goes on the left side of the tilde. And on the right side, I'm simply going to put a 1. And then we're fitting this to the estimation data. Okay. Aha. It is rating with a capital R. I'll only make that mistake once. Okay. So let's have a look here. So if I just type mod 1, that's what we get. So this is an intercept only model, but this is an important model because it kind of provides a baseline. Like if we can't beat this model, why are we even using a model? So I would note that if I did the mean of the estimation data, this rating variable, haha, autocomplete, not gonna do lowercase r there. This number looks a lot like this number. In fact, what's happening here is we're not returning model 1, we're printing something about model 1. If we specifically request a little bit more detailed information, say like, I want the coefficients for model 1, hey, look at that, they're the same number, less rounded. Okay, so this should really be jogging your memory from previous linear model experience to say that when you fit just an intercept only model, the estimate of that is literally just the sample mean of the response variable. So, well, I want to make predictions with this model. And it turns out that it doesn't matter what new data you give me, it's going to predict this, but I still want to look at the predict function. So the predict function is going to be the absolute workhorse of this course. That should be no surprise. We're doing predictions. We need to predict. There's a function for doing that. Okay, great. So I want to make predictions with model 1. And I want to make those predictions on the validation data. So what this basically says is take the regression function that we learned with model 1 and make predictions on the validation data. And when I run that, we do indeed see that it predicts the same thing for every observation. Again, unsurprising because we're not using any of the features. Okay, but I want to be very specific here. So I'm less interested in what's being predicted than how many things are being predicted. In this case, exactly 64. And now I'm going to do something. So now I want to predict mod 1 data equals val. And what happened? Wait, no, this is bad. Because now it's saying there's 256 predictions. But the validation data set only has 64 observations. What happened? What's gone wrong? So this isn't me making a mistake. This is me purposefully making a mistake, just for the record. You might notice something. That 256 number I've said before. It's the number of observations in the estimation data set. So if I went back and did this, predict model 1 estimation, I get those 256. Did I run that? Just to be sure. I ran it. Okay, 256. Great. So why would this code here return what should have been returned when I did this for the estimation observations? Well, that's because you've fallen into a trap, which is that the second argument to the predict function, when you supply something that is a linear model, is not data. It's new data. So when we do this, it works correctly. But back to this, when we did this, basically what happened is R goes, well, okay, you want me to predict based on model 1. I don't know what this is. Don't show me that. And what it ran was this. And by default, if you don't supply new data, it predicts on the data you use to fit the model. So that's what's happening here. So a strong piece of advice. I'm gonna look at the camera and really talk to you for a moment. When you use the predict function, don't name the second argument. Don't do it. Don't do it. I could talk right here for the next 5 minutes telling you not to do this. You're gonna do it someday. But hopefully you remember, oh, that Dave guy, he's crazy and he yelled at me about this already. So now I know what happened. So the issue that we're going to run into is that right now, when we're using the predict function, this argument is new data. Later, it's going to be data. And that's going to be incredibly confusing. So most of the time, I like it when you supply argument names like this. And because this would have been the same code, but this is just more informative. But my one exception to this is never supply a name to the second argument of the predict function. Why is that? So I don't want to get too far into the weeds on this, but if we look at the documentation on the predict function and we read it, predict is a generic function. The function invokes particular methods which depend on the class of the first argument. So if we look at the class of mod1, we see that it's LM. So what that means is the function we're running when we do this is not actually predict. It's a particular predict function, which in this case is predict.lm. And then we see, oh, here's the... I'm going to turn off my video for a little while. Or let's put me like tiny right here where things can't go wrong, right? Okay. Backing up. I don't remember what I did. Predict. Predict is a generic function. The function invokes particular methods depending on the class. We determine the class of mod1 is LM. So now I want to look at predict LM. And now here is the actual function we're running. So it takes an object, that was the model that we fit, and then the new data, that's this validation. Okay, deep breath, deep breath. All right, so I can say this, but I need to say one more thing. Where this is going to come up is someday you're going to make a prediction, and then you're going to compare it to a different vector of a different length, and R is going to give you this warning message that says something to the effect of like, inputs don't match. They don't have the same length. You sure you want me to do this? And that's when you go, oh, this is why Dave jumped up and down and screamed about this. So to recap, do not ever name the second argument to the predict function. Okay, deep breaths. Okay. So this was making predictions with the validation data. So, hey, why don't we see how well those worked? So why don't we do something like take the validation data and the ratings, the real ones, right? Let's look at their difference. Let's square those things. Let's average them. And then let's take a square root of them. Excuse me. So what I've done here is created a root mean squared error, in particular a validation root mean squared error based on the data that I supplied for that model. So this is our sort of our first pass of assessing how this works, and we're going to compare it to the other models. Couple things here. So this 140. So a question I'll inevitably get asked is, hey, is this a good root mean squared error? To which I'll respond, I don't know. Like, who knows? So first, this is a baseline. Like, if we don't do better than this, then the regression was all for naught, and all we needed was the response variable, and we could have made predictions. I mean, as good as possible anyway. But let's consider some things, right? So let's look at the range of that variable. Let's look at it in the estimation data set. So these credit scores, at least in this world and data set, go from 93 to 982. So we're on average off by 140. I think that seems kind of large relative to this. And I think if we look at another way, if we sort of look at the variability here, like this is, you know, it's you know, I'm flirting with R squared, even though I'm not going to talk about it. Like, it's really just not reducing variability there all that much, which is not surprising because these are very similar things. Okay, so so we got to do better. So let's fit some more models. So I'm gonna do so. Oh no, before that, actually, let me check my notes here. We've been talked about that, talked about that, talked about that. Okay. So this is something we're gonna do a lot. So this is something we should probably write a function for. So let's write a function. Let's call it calculate RMSE. It's going to be a function, and it's going to take in two things, a vector of real values and a vector of predicted values. And what it's going to do is it's going to say, take the actual values, subtract off the predicted values, square those things, average those things, and square root those things. All right, so now I've loaded my function. Let's test it. So we'll do, I don't know why that happened, calc RMSE. Actual is in this case, the y values from the validation data set, and then the predicted is this bit here, like this. So predicted from a model fit to the estimation, tested on validation. Okay, we get the same thing. And for the sake of what I'm about to do later, I'm going to do that. So function to calculate RMSE. And this is, so what we're doing here is we're calculating validation RMSE. Okay, don't need this anymore. All right, more models. So mod 2, let's throw in a variable. And I think balance was one of those possible good ones. If you remember that Paris plot we looked at, I'm also going to look at, let's see, rating, it's a function of balance plus income plus limit. I think those were those three variables we identified. And again, we want to fit this to the estimation data. So the fourth model is going to be rating as a function of everything, data equals estimation. So this just says, well, use all available variables that aren't this one. And then mod 5, I'm going to do something silly. So let's do rating like this. I just noticed this. So this will fit a model with rating as a response, all possible variables besides rating as features, and their two-way interactions. That's a huge model. So I'm going to go ahead and wrap that in step, which will automatically take that model and then get rid of some of the variables through an AIC selection procedure. And because I don't want to see it as it computes that, I'm going to do this. Okay, so let's run these, see what I got. I can't spell. Okay, got it. So like if we look at this model, we see, look at all these nice predictors. If we look at this model, we see a ton of stuff, but this is the resultant model. It has a lot of main effects plus two-way interactions. Oh, let's look at this model again for a second. Notice, like for the married variable, we have a dummy variable that's created for us. Ooh, I'm gonna wave my hands again. So because we did we sort of adhere to this rule that we want either numeric or factor variables, it makes our life easy when we use this, what we call formula syntax in R. So because I use a categorical variable, I need to do a dummy encoding, but it does it for me. Work smart, not hard. Let R do that for you. There's a bit of reading about that in the book. Have a look at it if you don't remember quite how that works, but please do not make dummy variables yourself. Just let R take care of it. Okay, so now what I want to do is calculate the validation RMSE for all of those. And here's one way to do that. Oops. And then I'm going to clear this, and then highlight this, and then do that, and there we go. Okay, so first model, RMSE, validation RMSE. Second model, validation RMSE, a little bit better. Third model, validation RMSE. Fourth model, validation RMSE, better yet, best one. And then fifth one, a little bit worse. One thing I would note, if you recall your previous classes on this subject, these models are, well, based on the result of this one, but let's just talk about these four because we know it for sure. These are nested models, so that's something you should think about. And this business where it went from here to here, it goes down, from here to here, it goes down, from here to here, it goes down, and then it goes back up. We're going to talk about why that's happening. There's a really good reason for that, and let's talk about that next week. But for now, that means that, well, we like this model best. So what I want to do is fit a final model. So that is what I want to do is I want to refit this model. We'll call it mod final, except now I want to fit it to the training data. And now what I want to do is repeat this process, but now I want to calculate test RMSE. So this needs to be the test set, this needs to be the test set, and this needs to be this model. So just to be really clear here, the y's that we're inserting into the RMSE function are the true y's from the test set. The model that we're supplying was fit to the training data, and the data that we're making predictions on is the test set. Okay, and there's our final RMSE. So these RMSEs, the validation RMSEs, we use to select a model, in particular the fourth one. This RMSE is what we say is, well, this is what we believe is sort of the type of error we're going to make on future observations. But let's do that. But this is just a number, right? And like we said before, if we look at sort of like the range of possible values here, you know, from like probably 0 to 1,000, I think is probably the scale here. 10, that's pretty small. So this seems good. But let's look at this visually. So I want to look at what's called an actual versus predicted plot. And it would take me far too long to code up this plot. So what I'm going to do is steal my own code. I feel okay about it. I wrote it, so it's good. Except this needs to be test, this needs to be test, and this needs to be this. The plotting code is not all that interesting, but there it is. So we see we're plotting the true values in the test set here, the actual the predicted values here, and we see that they fall on this line pretty well. This is possibly the nicest actual versus predicted plot we're going to see all semester. One of the more common things we'll see is small errors here, larger errors here, meaning the larger the predicted value, the more error there is on it. Now, that doesn't say, well, we shouldn't use this model to predict, but that's something we need to be aware of. So something to keep in mind. Okay, so okay, so sort of concluding the analysis real fast. Two things. I would say that if this were real data and you were okay doing this potentially illegal, potentially immoral process, it seems like you can make pretty good predictions to get away with this. I would like to throw caution here, though. I think we made a horrible, terrible mistake. If we go back and think about the variables that we included, right? We included this variable here, the limit, right? So this credit limit variable, and if I go back, and let's go back to ISLR credit to look at this data, credit limit. So it's hard to say what this really is, right? But this seems to be something that we might not have. This may have been something that came along with the credit rating that we purchased from the credit agency. So that might throw a wrench in this whole plan, meaning that this whole model we just built hinged upon the fact that when we go to predict new observations, we have this variable. But I'm kind of worried now that we might not, because we might not have that information. So I did this purposefully to say that one of the most important things about your models for actually using them is you have the feature variables all have to be things that you have when you go to make predictions in the future. Otherwise, you can't make the predictions. That seems silly, but someday, somewhere, I bet you will run into this issue where you get this really good looking regression. It's like, oh, I can make really small prediction errors. Oh, but I use data that I'll never actually have access to. So something to keep in mind. Okay. Last thing I want to do is I want to say I'm not a fan of this, and I'm not a fan of this. There's this phrase in programming called "don't repeat yourself." Well, I see a lot of repeated code here, although I'm not gonna worry too much about this one. I see a lot of repeated code here. This is the same code with 5 different numbers. There's got to be something, but like this is a recipe for disaster. Like too much copy paste. So what I want to do is sort of look at a way to do this where we don't have to repeat ourselves all that much. Okay. Okay, so what I'm going to do is I'm going to create a list of my models. I'm going to need to put some commas in here. Okay, so now I have this model list. So if I do say mod list 3, that returns my third model. I could also do mod list $ mod 3. That would also return my third model. Minor note, if I do mod list 3, which is a single bracket, that returns a list which contains my model. Not as useful. Maybe I should do a whole video on lists because I think that's something that needs to be refreshed. But for now, we have a list of models. So I want to repeat some things with this model. So one of the things I want to repeat with this model is for each of these models, I want to make predictions on the on the validation data. So here enters the lapply function. And when I hit tab, because remember we learned we're just going to hit tab all the time, it kind of inserts what they call a snippet in our studio, and it tells me what to do. So here I want to put a list. Well, here's the list I want to put. And the function I want to run is predict. So what did this do? It's hard to see. So it returned a list with 5 vectors as elements. And so what it did was, basically this code here is equivalent to if I did predict mod 1 like that, except I would have to store it as a list. So let's do this. Okay, so this and this are equivalent. So hopefully that kind of makes a little bit of sense. So the L and lapply basically reminds you that it's going to return a list. Sorry, I'm going to do a little bit of this. Okay, except what we want to do is to put est like that, right? So this is the code we... Oh, wait. I'm going to show off. Oh, wait. No? Oh, you're kidding me. Why is my cursor locked like that? All right. Ignore that. I had win lock on for some reason. I'm going to do this. Aha. Yeah. All right. What I want to do is... except this should be validation. Sorry. This is what I want. So basically, what I need to do up in this world, instead of just the function, so each element of this list is going to be made the first argument to this function. So if I need to supply other arguments to that function, I just do comma those arguments. There we go. So I'm going to call this pred val. So these are predictions on the validation data set stored as a list. So if I did something like pred val model 3, so these are predictions based on the third model on the validation data. Cool. Sorry, I've been talking way too long. Okay, so now what I want to do is take those and calculate root mean squared errors. So I want to do, let's see, an lapply. So now the list that I'm going to sort of operate over is pred val. And this time I want to do calc RMSE. And calc RMSE takes two arguments, right? So an actual and a predicted. And if we look at calc RMSE, oh gosh. Wait, sorry, I want to look at it. The first argument is actual, the second argument is predicted. So what I'm going to do is I'm going to now, after the list, after the function, I'm going to say actual equals val $ rating. So now this is saying, well, to this function, this is the actual argument. So then when it goes to look at each element of this, it'll skip over actual and go to predicted. Now, in this case, it wouldn't actually matter because if you flip where these are, it's the same, but I just so you know. Okay, so, well, here's that RMSE we saw previously. Here's that RMSE we saw previously, and so on and so forth. Except this is a list when really we'd like these 5 numbers to be in a vector. So that's where the S apply. So the S there stands for simplify. So this could be simplified from a list to a vector. There we go. I should probably talk a lot more about this idea of using the apply functions. I should also talk about using the map function from per, which is an alternative way to do the same thing. And I should also talk about how all this relates to trying to avoid for loops. For loops get a bad rap in R. People say don't do them. I'm going to say don't use them. But I want to note that one of the knocks against for loops is they're slow. That's not correct. Poorly written for loops in R are slow. Well-written for loops aren't going to actually be all that much different from this. There's actually some internal looping going on with these functions, but I digress. The main reason, in my opinion, to use these lapply and sapply functions is that it makes your code less likely to break and be potentially more readable once you sort of get used to it. But if you're comfortable with for loops, by all means, if that's how you get it done, get it done. But I would suggest you start learning one of these frameworks. Deep breath. Okay, I'm going to check my notes real fast. Yeah. Okay, so this was a long video. I sort of suspect that this will be one of the longest in the entire class, but we introduced a lot of stuff. Hold on, if I'm going to talk to you, I should make myself a little bit bigger. Hello. So yeah, we introduced a ton in this video. We, talked a lot about the LM function. We talked a lot about the predict function. We talked about data splitting. We did the data splitting. We introduced this idea of lapply, sapply. This is a lot. Excuse me. A lot of what we're going to do going forward is just sort of like mixing, matching, replacing different elements of this sort of larger process that we just did here. So sorry this video was so long, but I think it helps to introduce all these things at once. Pause, rewind, watch certain parts again, watch it at double speed. I watched a previous iteration of this video at 1.5 speed before I made this one. So yeah, gotta stop talking. All right, so as always, if you made it to the end of this video, good job, and I will see you in the next one.